I have the pleasure to present you to Sarah Gibson. Sarah Gibson is going to present No Magic Added, deploying multiple JupyterHubs to multiple clouds from one repository talk on behalf of the Try2C team. So thank you.
Thank you, Damian. Yeah, so hi, I'm Sarah Gibson, but I am presenting today on behalf of the Try2C engineering, site reliability engineering team, who are all of these lovely people on this slide. And also, there is a blog post that is basically this talk. So if you're like, I need to not listen to more people speaking, I'm going to go get a coffee and read this, you can probably visit that URL, and there'll be minimum information loss. However, if you're like, I want to see somebody get really, really overexcited about CI/CD, then you're in the right place, because this is my jam. So I'm going to talk to you about how we, how do we deploy multiple JupyterHubs to multiple clouds from a single repository without doing magic. So first of all, let me just describe a little bit what Try2C is. Try2C is the International Interactive Computing Collaboration. I've been working with these for almost 2 years, which is why I'm so good at saying that acronym. It's a non-profit, it's fiscally sponsored by Code for Science and Society, and we are a service provider for providing interactive computing infrastructure to research groups and education groups across many scientific domains. We also act as a collaborator for these researchers and educators to access open source development in the space that they are working in. And we contribute to open source and try to support the communities that underlie the stack that we are deploying. And as a result, in trying to build this vision, we have collected together a whole team of people that have many, many years of experience in interactive computing infrastructure for research and education, spanning all of these projects. So our main product is a JupyterHub distribution as a service, where we manage cloud-based JupyterHubs for research and education purposes. We run them with entirely open and community-led tools and standards to the point of which you can. At some point, you've got to rely on someone else's server, but for what we can control, we go with open source. We run these in a transparent and collaborative method. We have a shared responsibility model that invites participation from the communities we work with to help them, shape their infrastructure, because it is their infrastructure. We are just managing and operating it on their behalf. We develop shared configuration so that we can deploy across multiple communities, and this involves finding common workflows and distilling down beyond what is the domain speak to what is infrastructurally what is actually happening, so that we can share workflows across many communities. And we develop these features in partnership with open source communities and upstream as much of the infrastructure we need to achieve these as possible. So you end up with these two feedback loops of the communities of users in research and education and the open source communities that are developing the stacks. One of the really important parts of Try2C is we have a document called the right to replicate. And this gives the communities the right to replicate their infrastructure in its entirety elsewhere with or without Try2C. And this is the idea of using as many open source tools in the stack as possible, such that if someone says, hey, the service that you're relying on is not going to exist tomorrow, okay, we can pick this stack up, move it somewhere else. It doesn't have to be as disruptive as making new contracts with different cloud vendors and such. And what this looks like in practice for engineers at Try2C is we make commitments in how we design and implement and contribute the infrastructure we manage to be as open as possible, as transparent as possible, as upstream and maintainable as possible as well. So to actually get onto our infrastructure, we have a source of truth, which is our infrastructure GitHub repository. And it's made up of three main components. The first one is something called a Helm chart. If you don't know what a Helm chart is, that doesn't really matter, but it's a way of transferring configuration to scalable clusters. It's based on the community Helm chart 0 to JupyterHub on Kubernetes. And our Helm charts represent generalized config for education and research hubs. So we have a base hub that is everything we believe right now an education community needs for a collaborative distributed platform. You can extend the base hub up to what we call a Dask hub, which includes a lot more scalability and contains what we believe everything a research group right now needs from an interactive collaborative platform. The next piece of our infrastructure is config. And these are extra values that are, and extra pieces that are specific to each community. And this mostly represents how do you log into the platform. And that can be GitHub, that can be CI logon, or with your Google account. So because these are communities, you need to be a member of that community. So this config level, there are some other things in there, but it's mostly how do you log into this hub. And then the last piece of infrastructure I'm going to talk about today is a Python package that we call the deployer. And this is how we handle authenticating to cloud vendors, multiple cloud vendors, without every engineer having to remember exactly which project each hub is run on. There's a little shortcut. And it also handles upgrading the Helm charts for each cluster as well. So we had an engineering problem. And there is a very good reason why this screenshot is really difficult to read. Because even if we were in the GitHub browser and I had this full screen and zoomed in, this would be very difficult to read. It was a confusing config. We had a system where we had a single file to describe a single cluster, even if there was more than one hub deployed to that cluster. And all of the individual configs that I showed were in a folder beforehand were in a list, all appended to the bottom of this ginormous file. Now, if we're respecting the right to replicate, if a community should be able to come along and take their infrastructure and move it without our help, how on earth are they going to extract it out from this monster file? They're not. So that's already mistake number one. Mistake number two is engineers get eye strain. And the other knock-on effect of this is we had a very long-running continuous deployment pipeline in a privileged order. So there was no way to edit config for a single hub in a single file and only have your continuous deployment process touch the relevant hub. If one of the hubs in the line failed, the next hubs wouldn't get the upgrade, even if the change was unrelated to those hubs. And every time you append a new hub to the list, your CD runtime increases linearly with n. So we had lots of engineers babysitting really long-running pipelines. This was a problem and was going to prevent us scaling. So how are we going to solve this issue? Our goals were we wanted to be able to upgrade a specific hub in isolation if the changes we were making did not need to propagate to all hubs. Any of our production hubs should be upgraded in parallel, regardless of what cluster they sat on. and we wanted to use staging hubs as canary deployments. So you deploy to your staging hub first, and if your deployment fails, you don't deploy to prod, because production is where your users are. You fix staging first and go through the cycle again. But we wanted to achieve all of this while maintaining and respecting our community's right to replicate. So what do we need to be mindful of as we're working towards this goal? First of all, the deployer module. It is a convenience module for engineers. You saw my title slide. There were not many names listed on it. And yet we are running over 50 hubs. We have a high ratio of hubs to engineers. In order to scale, we need certain convenience functions to automate things for us. But that automation can't do anything that's going to fundamentally change the config in a way such that a community takes their config away and misses and loses a feature because they're not running it with our deployer. And that is what I mean by magic. There can't be processes going on in the deployer that affect what gets deployed such that if you remove the deployer from the equation, you can no longer replicate exactly. Now, there are layers to right to replicate here, and there's like arguments that maybe communities are running multiple hubs. But for this like first iteration, I wanted to assume that a community would have one hub and they wouldn't need an overpowered module to manage this hub for them. But we do need to solve for an overcommitted engineering team who don't have time to babysit long-running CI/CDs. So the first step we did was to separate out the config. Instead of one file per cluster, we now have one folder per cluster. And we have an approximate rule, and a guideline, if you will, that there is roughly one config file, values file, describing one hub. There are exceptions to this. Often staging and production pairs have a lot of shared config, and you're just changing the login. So you often have common config, and then a staging and prod that just changed the login redirect URI. And we also allow encrypted files to pass sensitive config. We introduced a cluster file, and this is the cloud metadata for the cluster. So which vendor am I running on? What's the project ID? Where's the key that I use to log in? And this is what the deployer reads to be able to manage this cluster is on Azure, this cluster is on Google, this cluster is on AWS. This file also contains the canonical list of hubs that belong to that cluster, and importantly, which files describe that hub. So then you can concatenate those files into a Helm upgrade command, which SRE that was just in charge of one hub is much more likely to run Helm upgrade, here's my list of files, than use a deploy like this. So this separation improves our right to replicate. It's much easier to know which files describe your hub and extract them, because there's a naming convention as well. So the screenshot I'm displaying here shows like a dedicated cluster. There's only one staging and production pair running. But we have shared clusters where the names of the communities are also included in the file path. But even then, that information is also encoded in the cluster.yaml file. So here is an example of that cluster.yaml file. In the green at the top, we've got the cluster information. Where does it live? How do I log in? And then you can see the yellow box is the staging hub, which maps onto the yellow boxes over here. These are the files. The red box is prod. The files are highlighted in red here, and then we have an orange common. So we can see how these files fit together to build the configuration. And as far as the right to replicate goes, like, this is an improvement. We have achieved our goal of maintaining right to replicate and making it easier for people to establish what their hub is described by. But this doesn't solve overcommitted engineers. So let's move on to CI/CD. So the first thing we need to do, we want to identify changes to isolate deploys. We want to be able to deploy one hub because its files have changed and not need to go through a whole list and do everything else. So there are two types of changes we need to understand here. The first type is like core changes that are going to apply across the board. This is like those Helm charts, that base hub and dask hub that I was talking about. If changes happen in there, that needs to propagate to all of the hubs. However, changes in common.values.yaml, changes in prod.yaml, those are specific hubs, and we need to be able to isolate that down. So we need to be able to differentiate before those two things. So what we did was we wrote a new deployer convenience function, where you can extract a list of hubs and the clusters they live on to redeploy from the list of created or modified files in the context of a pull request. So you can pass a list of files, and this you go through this workflow of saying, do any of these files belong to a Helm chart? No. Okay, we're not going to redeploy everything. Of the files, which cluster do they belong to? And you use file path inspection to figure this out. And you output a list of the cluster names and the hub names where the file changes have occurred. The reason we do cluster names and hub names is because they're the inputs into the other deployer function that runs the upgrade. And you can then, once you have your big list of everything that's changed, you then split that up into, okay, did I touch something in staging? And did I touch something in production? And if I touch something in production, is the corresponding staging reflected? And what we do is we create two JSON formatted outputs that describe prod and staging. And the JSON formatted outputs is going to be important because now we're going to get onto defining our pipeline. This is the coolest thing I learned during this project, because if you have a JSON output that you define in one job, your next job that can depend on your first job, and use that JSON output to dynamically define a matrix run strategy at runtime, which blows my mind every time I say it out loud and is like one of the coolest things I've ever learned. So we are creating dynamic parallel matrix strategies at runtime just by building a JSON object. And then we can run two jobs. We can run a staging job that redeploys the staging hubs in parallel across clusters, depending on which staging hubs need to be updated. And then we run a production job where all hubs get upgraded, all production hubs get upgraded in parallel, independent of what cluster they're running on. Okay, but now what if staging on one cluster fails? We still want to run production on cluster X, even though staging on cluster Y has failed. These are interdependent, these are not related systems. We still need to run that. So we have an inside filter job that filters away the failed staging deployment so that we can continue on to the good production. And this is kind of what it looks like in GitHub Actions. We have the first job that creates the two JSON objects. We run our staging job. We then filter out failed stagings and then run production. We also get a bonus convenient workflow because we have JSON objects now, and you can convert them to markdown tables. And if you run them in pull requests, you can then use the GitHub API to post those pretty markdown tables as comments on the pull request, which now gives all of the engineers an idea of the blast radius their PRs will create before they merged the PR, and also without having to go through really dense logging. So we made one significant change, which was we restructured the config that describes our deployed hubs, and we managed to achieve two things. We protected our right to replicate by producing less confusing config. It's easier to identify which config files relate to which hub, and it's easier for communities to extract their hubs and files. And we optimized our CI/CD deployments for overcommitted engineers. We isolated hubs from one another, only upgrading those that need it. We removed the privileged deployment order by parallelizing over the hubs, and we provide feedback on how the changes affect the infrastructure. But this alone actually isn't the end, because it's not an absolute protection of the right to replicate. Going into those cluster.yaml files is actually not that accessible. And even if a community did extract their files, they need to know what to do with them once they have them. So we need some community-facing document deployment guides that don't rely on the convenience functions or the magic that 2I2C engineers rely on in order to scale. So thank you very much for your attention. If you'd like to talk to me about this subject more in depth, I have a Calendly link where you can book a slot with me, and we'll meet for coffee out in the front of the conference and have a chat. And I'm very happy to take questions. Thank you.
Thank you, Sarah. OK, we have a few minutes for questions. Any questions? OK. I have a question.
Yes, darling.
Yeah. What's next on the automation? I mean, what will be the thing that you will like to see now that we have this system working?
So the question is, what would I like to see now that we have this system working? I don't know, is the answer. Mm-hmm. I am now no longer sure that deployments are the bottleneck on scaling, if that makes sense. Mm-hmm. So I think there's probably areas outside of our deployment pipeline that need improvement. Not immediately coming to mind, but that's because probably everything is coming to mind. But yeah, I'm always happy to be playing around with CI/CD, and especially if I get to abuse an API as well. That's like the ultimate way to make me happy. So you could probably convince me to do just about anything.
Thank you. Any further questions?
No, I managed to explain a technical talk perfectly. Amazing.
OK, thank you.
Thank you.